Hi, I'm Luke Smith from Build Test Solutions, and my talk today is to introduce pulse as a technique for measuring the air permeability of buildings. In terms of us as a business, Build Test Solutions, we exist to make building performance measurement mainstream. So to that end, we develop, validate, promote, and sell novel building performance measurement tools and techniques. Before I get into the detail of pulse itself, I just wanted to provide an overview of why I think air tightness is important. Uncontrolled air leakage typically accounts for about a third of space heating demand, so it's not trivial in contributing to both the energy efficiency, CO2 emissions, and running costs of our homes and buildings. By its very nature, it's air movement, so it's influencing both the comfort and well-being in our spaces. It plays an important role in influencing the ventilation strategy of the building as well, so it's an important balance to be struck between air tightness and the decision between mechanical or natural ventilation and subsequently kind of how effective that will be in operation. It's of course then also influencing both the health and indoor air quality of a building. It's both the infiltration and exfiltration of pollutants from inside and outside in a building. So it's again, understanding the air permeability is really important in providing healthy, good quality spaces. And it often actually manifests itself, or the issues obviously manifest as quite visual problems, so things like damp, mould, condensation, and to some extent also it has a bearing on overheating. And my view is that for all of these factors, it's important that we understand air leakage in buildings, air permeability under ambient conditions, and until now that simply hasn't been practical to actually do. So just providing an overview of the available methods then, we've got the low pressure pulse technique, which is obviously the subject of this presentation. We've then got the blower door fan that's well known and has been in circulation since the 70s, and then tracer gas decay testing. They're all ultimately seek to measure the same thing, so an air leakage rate at meters cubed per hour, but the key difference is the reference pressure at which they're making that measurement. So pulse is measuring directly at 4 pascals, and the blower door typically measuring in the range of 20 through to about 60 or 70 or so pascals, with the result often cited at a 50 pascal average. And then tracer gas is measuring the air leakage for the conditions of the day, so often the results are corrected for wind speed or temperature difference, and it's considered a direct measurement of infiltration on that given day. The costs are hugely variable, so tracer gas is quite a specialist activity, especially constant concentration type testing, and then blower door and pulse are kind of on a par when it comes to capital cost and the undertaking of the measurement itself. It's fair to say, I think, that no single technology serves all of these uses on the far right, but uses of all of these tools range from building regulation compliance testing, measurement of ventilation heat loss, measurement of background ventilation provision, or indeed to identify and address leakage points. More specifically on pulse then, it's a compressed air based system for measuring the air leakage of buildings directly at 4 pascals. Just in the image there, you've got the air receiver central to the shot, which is a 40 litre canister, which is used to release a burst of air into the building. You've then got the compressor on the right hand side, which is used to charge that air receiver up to a maximum of 10 bar. And then you've got the controller module on the left there, which includes a differential pressure sensor and is used to operate the test and measure the pressure response induced by the air receiver. And as I say, the main feature of pulse, the main innovation, is that it's measuring directly at those ambient conditions that are representative of real world as occupied conditions. By its nature, it's actually extremely simple to operate, and the results are easily obtained on the screen. Being low pressure, it's low disruption, so there are no service penetrations required through the envelope, so all the doorways are closed It's testing the building as a whole, so great for testing existing occupied buildings. And in the UK, we're approved for the method to be used for new build compliance testing as well as for retrofit testing under PAS 2035. Elaborating on the test process a little bit more then, the air receiver is placed centrally on the ground floor. Like I say, all external doors, windows are closed. The compressor is then connected to that air receiver, and the charge time is approximately 8 minutes from zero. Meanwhile, the operative can then go around the building, measure up and prepare for the test, so ensuring all internal doors are open, and depending on the test being carried out, they may choose to either seal over intended ventilation paths or indeed leave them open and test for the property in its occupied state. The operative then returns to the controller, enters the building envelope area and volume, and then it's a matter of quite simply pressing go. The execution of the test then takes approximately 10 to 15 seconds. The actual measurement phase within that is a fraction of a second. So the measurement is dynamic. So unlike a blower door, which is steady state, the fan is used to create pressure hold, and measurement is then taken once the whole building is at an equal pressure. Pulse instead releases a burst of air, and the controller then measures the pressure response within the environment. And the actual measurement is taken at what's referred to as the quasi-steady point. That is to say, when the airflow out through the air receiver is equal to the airflow out through the gaps and cracks in the building. So there's this momentary phase within the burst of air sequence that the measurement is actually carried out. The results are then presented immediately on the screen, can be saved and exported on a USB stick, and then we provide an online dashboard for analysing and generating reports from results and things. So I've touched on most of these already, but to summarise the main features and benefits, it's measuring directly at ambient conditions. So you can see on the chart there, you've got a typical blower door test with points ranging kind of, in this case, 30 pascals through to 80, and the results determined at 50 pascals through a power law curve fit. Pulse is instead taking a high density cluster of results, but cluster of measurements directly at low pressure. So the green circle there is like a cluster of pulse test results. You're able to measure the whole building envelope. There's no artificial stressing of the envelope. There's no need to do pressure and depressure. It's all done at a single low pressure burst of air. Very minimal setup, really simple to operate. The user gets immediate feedback and readout of results. And our field trials have shown Pulse to be extremely accurate and highly repeatable across a wide range of building types. The downsides, however, in being a dynamic measurement, you cannot use the device to locate leakage paths. So you've only got that instantaneous burst of air, so you're unable to track where the leak points are as part of the test process. And it could also be argued that it's actually a downside that you can't stress test the building envelope. You're not exerting high pressure or depressure on the fabric, and so you're not forcing convoluted leakage paths or pushing window seals or pulling loft hatches down. You're only testing directly at low pressure as a building would experience day to day, rather than kind of providing a stress test as such. And that for me is the key difference between the blower door and the pulse technique. It's not fair to necessarily play them off one another and compare them as like for like. They're measuring air leakage at two fundamentally very different pressure levels and providing very different levels of insight. To address the shortcoming in terms of leakage diagnostics, we also have our leak checker product. So this is our attempt really to challenge the culture in the industry, whereby we would advocate leakage diagnostics to be carried out throughout the build or retrofit phase, and that the test at the end is then one of compliance testing and to determine and understand the energy performance of the building, and only that. So it's not the point at which remedial should be carried out, and we shouldn't be finding out that a building's too leaky after all of the works is complete, and that all we can do to correct that is use some sealant or expanding foam. In terms of the journey that we've been on with the Pulse technique, it started out as an EPSRC-backed PhD and then some support from a EPSRC first grant. We then had some Innovate UK feasibility study funds to look at Pulse specifically at that point as a retrofit assessment tool. We then had some support from Bayes to carry out a large-scale field trial to directly compare Pulse and blower door across 123 different dwellings. The BRE then subsequently carried out what's referred to as an environmental technology verification exercise, which is a third-party verification to an ISO standard. There's also been lab testing carried out with the BRE, as well as a review carried out by the National Physics Laboratory. And Cambridge Architectural Research have kindly then summarised all the field work and all the testing and verification that has gone on. And all of this is available on our website, or by all means do contact me if you're interested in any particular aspects of this work that's gone before. And don't get me wrong, there is a whole host of potential further research that could be carried out. This is very much a new capability to measure air leakage directly at low pressure in buildings, and there's an awful amount for us to still learn. And then we've carried out a tremendous amount of market testing and key stakeholder engagement to inform the design of the product itself. Very quickly, in terms of use cases of Pulse then, clearly you've got new build residential, and using Pulse as a tool for carrying out quality assurance testing as well as compliance testing. I think it's fair to say there's a huge amount we really don't know about how our buildings behave under ambient conditions, and so we're all too familiar with testing at 50 pascals and then plugging those numbers into SAP using this divide by 20 formula to derive what that might mean at ambient levels or infiltration levels, and I think it's well understood that as a single value correction factor is not all that accurate. And so I think there's a tremendous amount to learn about how our buildings truly behave under ambient conditions, and perhaps in some instances buildings aren't quite as leaky as they might seem when tested under higher pressures. There's also retrofit, so air tightness testing has been far less prevalent in existing homes, regardless of the pressure level, so there's a tremendous amount to learn here as well. Use cases for Pulse and testing before, during and after works to determine both the air tightness but also the ventilation needs of a building, assessing that background ventilation. There's also using Pulse as a means of assessing specific upgrade suitability, so whether you're looking at promoting and selling draft stripping or ventilation systems, Pulse can be a very informative measurement in that respect. And of course there's a tool in social housing for understanding the root cause of mould and damp issues. Again, understanding that ambient background ventilation rate and whether the root cause is occupant behaviours or indeed particularly airtight fabric with inadequate mechanical ventilation provision. There's also use cases in non-domestic, so something I'm really keen to do more on is looking at room level background ventilation assessment. So in this COVID-19 age, assessment of classrooms, wards, office spaces, again understanding the background ventilation of those environments and whether then the mechanical ventilation provided on top is adequate. And also there's scope for daisy chaining, tethering multiple air receivers to create an even pressure distribution across large floor plates. So again, that's an area of further development for Pulse. There are also a whole host of specialist applications, so testing of clean rooms, containment labs, refrigeration chambers, server rooms, data centres with fire suppression systems, and so on. Again, Pulse brings quite a unique capability in not needing to penetrate the building envelope in any way, so it can be placed in an enclosure and set to test. And that concludes my presentation. Thank you. Please do get in touch if you've got any further questions or thoughts or ideas. We'd love to hear them. Thanks a lot.